a half comes from the integral. So, in that orthonormal series or orthogonal series, the only terms are possible, two terms are possible, only one term is possible, cosine, and the rest of the terms are all as part of the orthonormal series, but the corresponding lambda n's are 0. Okay. Similarly, if you take for this, right, if you take for this, you will end up with having a sin omega naught t is a solution, and sin n omega naught is also a solution, except the lambdas correspond that will be equal to 0. Are you with me? So, there are two possible solutions of a sin omega naught t and cos omega naught t is an expansion, possible expansion for this x of t is equal to some constant x1 cos omega naught t plus x2 sin omega naught t. Although there are possibilities of 2 omega naught t, 3 omega naught t and so on and so forth, the coefficients of that will be equal to 0. So, as far as orthogonal functions are concerned, they will be all sinusoids at a multiples of the fundamental frequency, but the contribution of those higher harmonics will be equal to 0, only these two terms correspond. Now, I can find what is x1 and x2 by doing integration, by finding out the correlation function for this and match with this, and it turns out to be x1 is equal to just check up at home, x1 comes out to be phi and t is one solution. Both are solutions to this integral equation, except that the corresponding lambda n is equal to 0 for n not equal to 1. And similarly, for this lambda n is equal to 0 for n not equal to 1. For n is equal to 1, x1 comes out to be equal to a times square root of t0 by 2 cosine theta, and x2 comes out to be a times root t0 by 2 sin theta. Now, if you substitute these two into this original equation, that means I am now expanding xt as equal to a integral t0 by 2 cos theta cos omega naught t plus a square root of t0 by 2 sin theta sin omega naught. This is the expansion, Cardinal-Loubet expansion for the given correlation function. Is it clear? It is a very trivial example, but very important, nice way to show how do you solve this equation. If you do anything any more complicated r and tau, big analysis has to be done to find out what is the current loop expansion. This is one very simple example, of course trivial example. Are you with me or not? So, since this orthonormal series only give rise to a coefficient corresponding to fundamental, nothing to do with this, so others are not appearing here. Only fundamental will have a coefficient which is given by this and this. And what is this equal to? To rewrite this by using the trigonometric relationships, xt comes out to be equal to a root T0 by 2 into cos plus or a minus here. It turns out, if you go backwards, if this is the description of the random process as a function of time, with theta being a random variable whose distribution is called uniform distribution, which means that p theta is uniform from minus pi to pi. If this is the random variable which is here, then this is a random process obviously, because the process built out of a random variable, so it's a random process, and depending upon what value of theta it will take, this will be different. Where it starts is a cosinusoidal waveform, but where it starts is a random position corresponding to theta. So, this random process has this as the correlation function which was given here. Without knowing that, I have been able to show to you that by using the Coron-Dubé integral, I am able to find out that the process should be this. In this case, it came out to be cosines and sines and matched with the actual process, but it is not necessary that any x of t would always end up into cosines and sines. It may be any functions. Only thing it is simply saying is that if you expand this x of t process, whose deterministic equation you may not have, the correlation function you arising out of that expansion will match the correlation function. I am not saying that the x of t you will get by expanding it into the orthonormal series is exactly the process that we have. We are only saying by doing this expansion, the resulting expansion will have correlation matching with the original correlation. But the form of the x of t arising out of this expansion and the actual process may be totally different. Is the point clear? Like for example, if you are given a time function and you expand it in sines and cosines using your Fourier series, is an expansion, but the function may have nothing to do with the sines and cosines, right? And the same spirit here, the process may be any x of t, a random variation. But what all I am claiming is, if you expand it in this manner, then the expansion will give you coefficients which will result into the correlation function corresponding to that process which you have started with. It is a very simple, nice example to show how to expand it, how to solve this equation. If you go anything more complicated RXT, then the solution becomes a very complicated solution.